Welcome to Distance, Rate, and Time Problems. We're in section 4.8 of your book. This is something that we've actually looked at a few times sort of informally in class. And now I want to show you a bit more formally how you might approach problems that have to do with distance, speed, time. It's very similar to some of the things that you've been working on in physics class, using velocity, acceleration, and position. Generally speaking, a distance, rate, and time problem is going to give you some information around time, speed, or distance. So why don't we label that in our formula here? So I'm just going to label, I'm going to say that D is for distance. Distance is usually measured in meters or kilometers or feet, miles. R stands for rate. Another word for rate is speed. And in physics, you've been talking about this being slope. Time is T, and we're talking about total travel time, like 2 hours in the air or 4 hours in your car. We're not talking about time of day, right? We're not talking about 12 o'clock or 4 o'clock. We're talking about total travel time here. Now, many times, these problems are going to have multiple distances, rates, and times to keep track of. And we could set up a system. We could use substitution, which is something we've been practicing a lot in class. But I find that there's a particular organization system that really helps me set up the equation to solve this problem correctly every time. So I'm going to spend some time with you just now looking at distance, rate, and time problems, specifically using charts to help us set up the equation. So follow along with me in your book. I'm on page 167, simply going through the examples that are listed there. The first type of distance, rate, and time problem that we might encounter is one in which two objects are moving in opposite directions. In the case of this example, we've got two bicyclists, Fian and Ella, are riding their bikes, and they start 60 kilometers apart. All right, already I'm thinking that I need a visual representation of this. So I'm gonna do a quick little drawing. I'm gonna say that we have got a bicycle here, right? And we've got another bicycle here. And they're moving, they start at 60 kilometers apart. So I'm going to say they start here at 60 kilometers apart. All right. Now, what else do I know from this? Okay. They meet at some point in the middle. Now, I don't know that it's exactly halfway in between. So I'm going to say, let's say they meet somewhere here. So this pink bike is moving this way and this blue bike is moving that way. And they meet somewhere between, in the middle of this 60 kilometers. Now, let's see, what other information do we have? Fian's speed was 4 kilometers per hour greater than Ella's speed. And we also have time of day. All right, so let's take a moment and gather all of this information in yet another method. All right, so for distance, rate, and time problems like this, I'm going to set up this chart. The chart is always going to have, in the first column, it's going to indicate the object that's traveling through space. So in this case, we've got Fian and Ella. They're the ones traveling. Here, in this column, I'm going to put their rate or their speed, time, distance. Now what I'm also going to remember is that rate times time equals distance, right? That's the formula that we were looking at before. D equals RT. Rate times time equals distance. All right, so now what I have is, let's see, I've got Ella. And the information we have from Ella, let's see, we have that she is going at some rate. We have no idea what her rate is, so let's just call it R. And she's traveling from noon to 1:30. She's traveling between noon and 1:30 p.m., so that's an hour and a half. So she's traveling for 1.5 hours. So her total distance, if I take rate and time and multiply them together, I'm going to say, let's see, rate times time equals distance. So her distance is 1.5 times her rate. So at this point, we actually don't know how far she went. We just know that she went at some speed for an hour and a half. I'm going to do the same thing for Fionn here. So we've got Fionn. He's our second person. He's going at a rate that is 4 kilometers greater than Ella's. So Ella's is R, and Fionn's going 4 kilometers per hour faster. So that's his rate. He's also traveling between noon and 1:30, so that's an hour and a half. So he's also traveling for 1.5 hours. Now, when I do the same pattern, this R times T equals D, R times T equals D, then I'm going to have something that looks like 1.5 times R plus 4. All right. So what I've essentially done here is I've organized all of my information so that I have these two expressions for distance. Okay, I've got Ella's distance and Fionn's distance. Now let me make a little bit more space here. Okay, so we're just going to remember that we know total, they started at 60 kilometers apart. So in other words, if I take Ella's distance and I add it to Fionn's distance, then I'm going to get a total of 60 kilometers. All right, so let's write that out. We've got Ella's distance plus Fionn's distance equals 60 kilometers. Now we're going to use some substitution, some nice substitution. We see that Ella's distance is in 1.5 here, 1.5 R. So I'm just going to write 1.5 R plus Fionn's distance, which was 1.5 times R plus 4, and that is equal to 60 kilometers. All right, so now I have an equation that I can solve for this. I've distilled all of the information from this word problem down into this equation. So once again, I'm going to give myself a little bit more space so that we can work out this problem. Okay, so you're doing some distribution. 1.5 times R is 1.5 R, and 1.5 times 6 is, 1.5 times 4 is 6. And now I'm going to combine like terms and move this 6 over to the other side. Combining the like terms of 1.5R to make 3R, bringing the 6 down and the 60 stays as well. Now what I want to do is get constants on the right side, leave the variables on the left. This looks like an equation that we're getting pretty good at solving now. All right, and then subtracting 6 from both sides, 60 minus 6 is 54. And then really quickly just dividing both sides by 3, I get that R is equal to 18. All right now. So let's see. Our original R represents Ella's rate. See the blue R here? So then in order to find Fionn's rate, first let's label that 18 kilometers per hour is Ella's rate, right? And then to find Fionn's rate, his was Ella's rate, 18 plus 4, right? So Ella's rate plus 4 is Fionn's here. So Fionn has a rate of 22 kilometers per hour. So my final answer is here. Ella goes 18 kilometers per hour and Fionn goes 22 kilometers per hour. And after an hour and a half, they've met somewhere in the middle of 60 kilometers. Okay, in class, we're going to go over this chart again for two different situations. We're going to talk about, rather than opposite directions, we're going to talk about same direction, and then we're also going to talk about round trip. Like I drive to the store and then I come back home. So tonight, just taking notes on this example, and then when you come into class tomorrow, we'll look at two other situations.